Okay, so welcome to the next lecture. Last time we started on the random linear network code, so the intra-flow network coding. And what we did last time was talking about the coding matrix that was filled up magically by random numbers, right? Which are random numbers of a finite field. And we told you at that time even that will work equally good as some design codes. Actually, it will work better, as you will see, but just understanding the concept of randomness in such a context is already strange. And then we thought, let's think about how to encode, decode, and recode packets. There was a new feature of this random linear network codes, which was recoding. The other feature that network coding will bring us here is the sliding window, so latency-related coding. Now, when we do the coding, what you saw last time is only you can code over different fields, right? I told you at that time it were a certain granularity of your randomness. The question is now, why should we go for different fields? I think with the butterfly we have seen that the binary code, 0 or 1s, is not so good because when you randomly choose A and B, that was not a good choice. If you do some linear equations coming to the node that you can recode, that was way better, okay? But on the other side, you also saw that when we do the coding on a different field than binary, it becomes a little bit more complicated, right? Already, binary was just XOR, but anything else than binary, we had to think about how to compute, multiply in fields, and so on. And today, I would like to start with a field size analysis. It's not only the field size, it also has to do with the generation, and it all started when we did our first implementation on the phones. So we played around with what we saw in the papers, and there was 2 to the 32, 2 to the 17, some only used 2 to the 8, the losers, so to speak, right? But implementing it on an embedded device, 2 to the 8 was already complicated, 2 to the 16 even more complicated. And the only thing that really worked on the embedded device at that time was binary. And one of the guys that we talked to next to Muriel Medar from MIT was Ralf Kötter at TU Munich. And he was also very much working on this random linear network codes. And when we told him, you know, the only good stuff is binary with a decent coding speed, he asked, how bad is binary? Good question, right? And we said with the butterfly, it's not really good. We had 2 packets. But what if we do other stuff, right? If we have maybe more packets to code together. Does this have an impact? And what you will learn today is the generation size. This is the number of packets that are coded together. You remember we had the coding matrix and next to it all the packets, and P1 to PG, this is the generation. So how many packets we code together may have an impact. And the field size, this is the number of elements of the finite fields that we have. Binary, 2 to the 2, 2 to the 4, 2 to the 8, 2 to the 16. And these 2 are the main drivers that have an impact on the performance in terms of linear dependency. So how good is your code? Overhead, this is the encoding vector. Or when you have to repeat packets or add more packets due to linear dependency, there's a secondary overhead. And then you have complexity, so what your embedded system has to do. So what we did is a very simple example. We took a sender and a receiver. And the sender was sending packets of a certain generation, and the receiver would just decode that. And every packet that we give over the link, there was no error whatsoever. So if you would not have a code, after G transmissions, you would be done, right? So what you see here is the probability of decoding after receiving 50, 51, 52, 53 packets of a generation of 50. So just to tell you, when you have 50 packets on one side and you don't code anything, after 50 time slots, after 50 transmissions, you are done. If you use a Reed-Solomon code, which has a planned code, after 50 time slots, you are done. If you do it randomly, now the question what is the probability of decoding after receiving 50? If you have a binary code, it's only 30%. If you get 51 packets, it's 60%. Then 50, 52, 80% more or less, and so on. So in order to have 100% decodability, you need something around 60 packets in the binary case. as it seems here. Now, if you have a higher field, 2 to the 2, you see after 50, it's already 70%. If you have 2 to the 8, it's higher. It's close to 1. It's not really 1, as you can see. And then you can say, what should we do here? And at the time when we looked into this and saw this one, we had in the theory part that small field sizes are resulting in linear dependent coded packets. So they should not use it, right? And then the large field size seems to have no overhead. Therefore, everybody in theory was saying, let's use large field sizes and even large generation sizes. Why this is important is something. When we measured this and said, what is the mean value here? We found out it's 51.6. So when you want to transport 50 packets over an error-free channel, you need 51.6 transmissions in order to get it to the other side. Mean value, as you can see from the distribution, what is the likelihood to send more, right? So what is this 1.6 extra, right? We looked into that and we said, okay, now let's have a model of that. We have a transmitter here and a receiver here. Here's a channel and a network with some packet losses. And we would like to say, when we send the first packet, here we have M, which is the number of packets that we still want to send, or in other words, encoding the degrees of freedom. So which ones will be linear dependent on the next one? And for the first one, it seems pretty easy, right? So if I send the first packet, in order to decrease the degrees of freedom, to make it a useful packet on the other side, what is the probability? When you have a certain number of packets and you randomly just say, I randomly put, let's say, a binary field. You have a binary field, you have zeros and ones, generation size of 50 as the example before. Now, what is the probability to go to the next state where you say, I transmitted one packet successfully? And why is there still something like this? Is there a probability that we send something that is not useful for the other side in the first packet? So what would you say? If you go to the Panini stand and you buy one picture for your album, is it useful or not? That's useful, right? Here, there's a small chance that there's not useful. What is this? If I take an encoding vector, let's say with G packets, which means G bits, and I randomly put zeros and ones, I could make a mistake by put all zeros. Okay? So this is the only one to stay here. In all the other cases, if at least one of them is 1, you go this way. So now you're here. What is the likelihood to go to the next one? So you should not send the zero, so all zeros, the null vector. This is clear. And what shouldn't you not send as well?
No, the linear combination you sent before.
Correct. In this case, I have only one, so not the packet before, but as you said correctly, from now on, never send the null vector, never send any copies or linear combinations of the ones before. And then you go in, after you go to the last one, you said, now I need one packet, more or less, to send to the other side, and then you're done. So this is a Markov chain, and we can calculate this. There is some analysis about it, and when you look into that, you get an equation that says the expected mean value for that is just the sum over 1 minus q minus to the power of k, where k goes from 1 to m, where m is the generation size. And for that, you can have an upper bound, right? You say, okay, in the worst case, if you have, this is the generation size, q is the field size. So imagine q is quite large, right? So if q becomes large, then this is more or less m, right? And this is m plus something, but it's the minimum of that. Right? If you say q is 2, this is 2, this is 2m. So there's the 2m over here, right? M just would be here. And something between m plus 1 and m plus 2 happens here. So you can estimate there's an upper bound m plus 2. Remember we had 50 packets that we want to convey, it was 51.6. So 50 plus 2 is 52. 52 is the upper bound. Yeah, that's okay for us. Can we get there a little bit better than m plus 2? So when we did the decoding, what we had were, for example, 3 packets. So this is just the encoding vector with the packets, right? So with that, what you would do is trying to do this kind of finding the pivot elements here and adding zeros here. What we did last time, we exchanged this line upstairs, we did the zeros below. You remember that? So when you only have 3 lines, this is a binary code, a generation size of 4, then doing all of that, you could say, okay, I create this 1, 0, 0, 0, 1, 0, 0, 0, 1. And then something is here which we need to still to clean up. So the next packet, the last packet that will come now, and we are here in this stage of the last one we would like to send, what packet would be good to clean this up? And this is given here. So what probability is to achieve a linear dependent linear combination? It's xxx1, which means it doesn't matter what is here, but we need a 1 here. What is the likelihood to get a vector exactly like this in the case of binary? 50%. So the last packet to be useful is 50%. Now, if you think about this, what does it mean for that one? So this was useful 50%, and the one before, you have 2 bits, right? And at least one of them must be 1. If more is okay, only 0, 0 is bad. So it's 25%. So if you go back like this, what you will find out is the more you on this one is quite likely to happen. But in the end, it will be always harder to end it up, right? Okay. So you could say, let's look into this Markov chain again. Let's assume we have this kind of behavior. In the beginning, it doesn't matter. The 0 vector here would be bad. As long as you send something that is not 0, 0 here, that is also okay, and so on. So if this is the binary field, it's 1/2, 1/4, 1/8, 1/16. If you have a higher field, it's just 1 over 2 to the 8. Why is this? You don't want to have a 0 in the last one. And the last one as a symbol would be only 0, all zeros, okay? And this is 1 over the field size. And the one before, 1 over the field size to the power of 2. So when you do this and you look into that, you could say, okay, this is the degrees of freedom. I would like to transmit 16 packets. I have a binary. And this is the extra packet I would send for the first one. Nothing. For the second, for the third, and so on. And now we're going towards the end. And you see, now we have to send, there's a likelihood of sending a little bit more extra packets. For the last one, for example, we send 1 extra packet because the chance of being useful or not is 50%. 1 over the probability is 2. So 1 we have to send anyway. 2 minus 1 is then 1 extra packet. And here's a little bit more, less, and so on. But if you sum this up, it's 1.6. So it's not really 2. It's 1.6. And not only in this case. This 1.6 exists only for the binary, not for the other codes. If you have a higher field, you will see later what the extra is you have to send. Now, is this always true? Is this always 1.6? And is this independent of the generation size? So we did some calculations over here. It's the overhead independency of generation size. It's a binary field. And you see that if the generation size is 16 as it was before, it's 1.6. So if you go back, then you see, oh, it drops a little bit. Why is this? Because you don't make the sum over all of them. You make the sum over this is 1 packet, sum over 2, over 3. So when there is more, it doesn't matter. So just what you have to have in your mind. It doesn't matter what kind of generation size it is as long as we are larger than, let's say, 8, right? It's always 1.6 extra packet. So if you want to convey 1,000 packets, the 1.6 packets does not hurt you so much. If you transmit 16 packets, 1.6 is already 10% extra, which is a lot. Okay, if it's 8 packets, it's 20% extra, and so on. So this, how bad is binary, depends a little bit on your scenario. If the generation is large, 1.6 does not kick in so much. So in order to test that, we have something here, notebook at deutsche-telekom.rocks. This is a Jupyter notebook where we put some code examples. So what you will learn here is also to use Kodo in its form of C++ and Python. And here we have Python example code in the web browser, which you can execute, where you can even change something. Is it working now? Not yet. Okay, so then you can try it later out. This is just what you will see there. You will see this is just copyright, and you can click play by one what happens here. Then you see, okay, we import something to give some data out. We have to import Kodo, which is the network coding library, of course. And then you say, okay, let me do it like this. I have symbols here has a different terminology, right? We use the same as we had in the IETF document, and symbol size. Symbols is another word here, they mean generation. 8 packets in a generation, and every packet has 160 bytes. So this symbols or generation equal to 8 has an impact on the performance. This one here, if you change it or not, will not have an impact on the examples we have here. The size of the packet will only have an impact how fast Kodo can calculate. The smaller you do this, the faster it is. But the result in what is linear dependent or not is always the same here. So this is how large in bytes are your coded packets. If you need IP packet, maximum ITU size 1,500, so it's totally different from that. And then what you see here is we create an encoder and we create a decoder. Okay? And the encoder is quite interesting. First we do an encoder factory, which is more like the building block. How should this encoder look like? What is this? Because we have different forms of encoder. You don't know it yet. We will come to that. But in this case, we say full vector encoder. This is exactly what you had. You have the matrix, and we are shooting in. It's called full vector encoder factory binary. Binary means really binary field size. So it will be an encoder with generation size of 8 and some 160 byte packets. And this is then we make the building block of it, and then here we call the factory build it. And now if you look at the memory, now the memory would show, oh, there's something built up. So we allocate memory to hold 8 packets by 160 bytes plus encoding vector that code is doing for you. You don't have to do it. And with this call, you have an encoder. And the other side is a decoder. You have to also need a decoder with the same stuff over here. It's all binary. If you want to higher fields, it's called binary 8 with the number 8. Binary 8 means 2 to the 8. Nothing else in that. And then you build a decoder. Now you have 2 decoders. And then what happens here is you say, okay, there's something to fill up the encoder with random data. I don't show it to you, something is missing over here, but what I want to show is when we then do, we want to understand how many packets we need to send in the case of binary fields. We just say, okay, packet number is 0. We call decoder factory build again. Why are we doing this? By calling it again, it's cleaned up. So there's no data in it. And then we ask, hey, decoder, is complete? So when you just call it, it's not complete, right? It will say my rank is not equal to the generation size. So no, I'm not complete. So you go in, you encode, you ask the encoder, give me a packet. And he will give you a packet. And this packet is a coded packet in the binary field plus the encoding vector. You can even print it if you want, right? And then you say to the decoder, read payload, and give him exactly the packet. So I take it out of the encoder, I give it to the decoder. Very simple example, right? And then you say packet number +1, and you do this until he will say, I'm complete. And then you remember the packet number, and you append it to a field of packet sent, which is just a field, and every time you say how many times you had to transmit it. Our generation size was 8, And sometimes it's 8, sometimes it's 9, 10, 11, and then it goes down in probability more or less. And when we do this, after you have done it 1,000 times, you calculate mean extra packets. It's a sum of packets sent divided float length of the packet sent minus the symbols. So what we really want to do is how many packets, all the packets sent over here, we make a sum of that, and wait a minute, these are the extra packets over then, because the number of symbols is 8, and we subtract this from here, and then you have the mean extra packets. And then you can print the mean extra packets just by calling it, and in this case it's 1.58999, right? If you increase this to 10,000, it goes up to 1.6, right? This is a fixed line that we write here. It should be 1.6. If you then take another encoder, then for example 2 to the 8, the extra packet is something like 0.001. There's an extra thing, but it comes later.